Okay, by now you should have seen the derivation for the constraint analysis equation. This big long equation that was derived here. I derived it for you in an earlier video, and Dr. Brandt discusses it in chapter 5 as well. I believe it's around page 300. It's also known as the master equation. And what I'd like to do for you is program this into Excel. So the first thing we're going to do is we'll go to JET, and we're going to grab the master equation here from the constraint tab of JET 10. And it looks pretty involved, but again, watch the derivation. I think you'll find that it is not too terribly difficult. We're actually going to build a constraint diagram like this one here. Now you're probably asking, sir, why do I have to build a constraint diagram by myself if it's in JET 10? Well, first of all, the pre-quiz and the homework assignment require you to have constraint analysis. Third of all, how do you know that your calculator's answers are correct, right? It's a black box. You type in some numbers and it gives you a number back. What makes you qualified to say that that's correct? Well, you've proven that it's correct. If you do 2 + 2 = 4, you can actually prove that. So you have confidence that your machine is working. How do you know that how black JET 10 is working? Well, we're going to kind of show you inside of the machinery, and you're going to actually program the constraint analysis equation so that you understand how it's working. And it's no longer a black box to you. You could actually go in and analyze some of the changes. So I've copy pasted the the constraint analysis equation here into Blackboard, and I will also be pre-formatting a few things, but this takes a little bit of time, so just walk through it with you, and we will answer the pre-quiz and/or the homework. So to start with, the first constraint is Super Cruise, and for Super Cruise, I'm going to populate the Mach value and copy paste it all the way down. Now, there's a lot of different shortcuts, ways to calculate or to populate Excel. I'm going to show you a few of them, and you'll see that for illustration purposes, for pedagogical purposes, I'm going to make some of these columns all of a constant. You could easily shortcut that, but for now, what I want to do is illustrate to you the entire column as a constant. So there's the Mach number for the speed of sound at 30,000 feet, which the question asks you to solve for. A, and let's be more precise here, A as feet per second. Okay, and what's our feet per second at 30,000 feet? 994. That's 8 from the back of the book. Of course you did. And now we're going to calculate it for V. Well, how do you solve for V? Velocity comes from the Mach equation in this case, where Mach is equal to V over A. So Mach times A gives us velocity. So we'll say equals A star Mach, and that gives us our velocity calculation. And of course, it's going to be constant all the way down. What is Q? Well, Q is equal to 1/2 0.5 times rho. Well, where's rho? I need to get rho from the back of the book. And for this condition, we're in English units, so 0 decimal, 1, 2, 3 zeros, 8, 9, or 1. That's 1/2 rho times V caret 2 squared. And bring that down. Now, I don't want this to go out to 5 decimal places, so I'm going to come up here to my menu option and shorten that down to something a little bit more reasonable. We'll put it at 2 decimal places. Let's not forget our units. Our velocity units are also in feet per second. And what is dynamic pressure Q? Q is force over area. So in this case, we're going to be pound over feet caret squared. Okay. What's our K1 value for this problem? I believe it's given in the problem statement, 0.224. And again, we're just going to copy that all the way down. And our K2 value for this problem, for this condition in supercruise is 0. Copy that down. And I'm doing this because what I'm going to do now is I'm going to go in and plug in this entire equation. And once that's done, all these values will be in there. We'll be able to test for the value. Now, we're at supercruise. We're cruising. We're not pulling any G's or anything like that. So we're going to say that our G load is 1. What's S? Our planform area. The planform area was given at, oh, right. I actually made an error here. Planform area is right here. Let me get I like to draw. Planform area is right here. We're going to keep weight takeoff over S as our ratio. Remember what we called that? That's wing loading. That's wing loading. So I'm actually not going to need an S column. So let's make that. I like to I don't mind making mistakes on these recordings because it shows you how easy it is to make a correction. Okay, so what's CD0? I think CD0 is also given 0 point 0.037 357. And I'm going to copy this down. And is CDX given? I don't believe so. I think CDX was 0 in this case. And G, 32.17 to be most precise. And what's the acceleration of gravity? Feet per second squared. And I already have G loading, so I can get rid of that. DHDT, well, that's a climb, right? I'm not climbing, that's 0. Am I accelerating? No, I'm not accelerating either. It's a super cruise condition. So let me type that in here. This is super cruise, which means I'm traveling in afterburner in a cruise condition level. All right, let me copy one more down. Okay. And I believe alpha and beta were also given. Beta is 1, and because we're not assuming a weight change significantly for that, our weight fraction is the same. What's our thrust lapse rate? Given as 0.717. Okay. And now we're just going to pick a ratio of pounds per square foot. Foot caret 2. You could type PSF if you'd like. Okay. So we're just going to pick a ratio. We'll just say 10, and we'll add 10 to each one of those increments so that we can have a wing loading that goes up by 10 to about 130. And again, we're just plotting a range of wing loadings from 10 to 130 to help build our constraint. This is one of the axes, if you will, of the constraint plot. Okay, so we've got Mach, we've got alpha, beta, we've got load factor. I have my CD0, K1, K2. I have my acceleration, my speed of sound at altitude. I've calculated velocity. I plugged in density. I calculated Q. I'm not accelerating and I'm not climbing. So those values are 0 as I read across. Okay. So now the trick is to successfully program this in, and it's a challenge. So you have to take time. So let's say equal, we're going to program all this thing in. So equals, let's take current, and just do exactly as it looks. So we're going to take beta divided by alpha, star, open parenthesis, Q, times S. But I don't have S. I said I got rid of S. But look, S and W are here. S and W are here. And you have S and W right here, wing loading, but it's inverted. So when you program this equation, you actually have to invert wing loading into your equation. So you recognize that, and we'll do so accordingly. And I think I lost my work here. Let me look over this and see if there's anything else I should mention before we go much further. So we'll say equals, open parenthesis, beta divided by alpha, star, open parenthesis, Q, times one divided by wing loading divided by beta. Okay. And I'm going to close that, star, K1 times N times beta times beta times wing loading divided by Q. Close caret squared plus K2 is 0. Okay, K2 is 0. But for the purposes of this equation, we want to copy that, or we're going to copy it. So we're going to record. We're going to make sure that we keep the information in there. So K2 times open parenthesis N times beta times wing loading divided by Q. Close parenthesis plus CD0 plus CDX, close parenthesis, plus 1 divided by velocity times dHdt, which we know is 0, plus 1 divided by the acceleration of gravity times dv dt. Oops, I didn't get my acceleration of gravity in there. I can tell because it's not highlighted. N15, it's in there, but it's not highlighted. Why is N15 not highlighted? And of course I got an error. Let's see, let me go up to the bar here. And it's saying that M15 didn't like how I did M15. CDX. Why doesn't it like M15? Let's assume it equals minus. You'll probably run into this. Well, you're probably actually a better Excel programmer than me, but I'm seeing that it doesn't like M15. There's a problem with this for not trying to type formula. Actually, I am. Okay, alpha, beta. Let me see if it'll work without this mess here. We found a typo. Did I miss a parenthesis? That might have been what it is. See how it took that parenthesis off the end? Let me, because I think I need another parenthesis here to close that one. So like that. And now I'm going to go back. Okay, so I was missing a parenthesis. So now I'm going to go back and I'm going to add, what I was doing was I was messing with this term here, CDX, that's where it was giving me the error. Now I'm going to go back and add these terms back in to my master equation. Okay, so now that that's in there, I'm going to say plus, I'm going to do 1 divided by velocity. Okay, now I'm getting the colored cell reference, so that tells me now it's working again. Times star dH dt, which is here. Okay, and then I'm going to add parenthesis 1 divided by the acceleration of gravity. See, now it works. It's highlighted times dv dt. And we close that. Whoops. Get rid of that. Let's see, it didn't like something. Okay. So now I have a thrust to weight ratio of 7.112. And I believe that is correct. Now, what I should be able to do is click and drag this down. And I get populated from. So now let me make this a little bit more reasonable to look at. I don't need all those decimal places quite that accurate. Okay. So there you go. I made a couple mistakes along the way. I kind of had to go back and recognize it. I kind of learned how to use Excel. If it doesn't give me the colored cell reference, that means it's not referencing. It doesn't see it. I made a mistake. We found that we left out a parenthesis. So that helped. All right, so how do you plot this now? I need to be able to plot this. And what I'm plotting are these two columns. So I'm gonna plot. You know what I'm gonna do also is I'm going to put my little grid lines in. I'm going to put that in and make it look a little neater. I've centered everything. That's just how I like to keep my Excel. I like to have things rather clean and neat. And I'm going to color. I'm going to give this a color. Let's give it like a light green. And then we'll give the wing loading, let's say like what's it, like salmon? Sure, that works. These are the two columns I'm plotting. I'm going to plot thrust to weight on the vertical versus wing loading on the horizontal. So the way you can do this really shortcut, you can just highlight these. You can insert a line. I don't want that one. I want the points but smoothed. This one right here. You want a scatter plot with smooth lines. So let's do that and check that out. But these are reversed. I said I wanted wing loading on the horizontal and thrust to weight on the vertical. So let me right click and I'm going to, let me see, select data. Yeah, let's do that. I'm gonna, right here it says switch row and column. Okay, so we did that. Let's check that. That's not what I want. Everything's on the right axis. Oh, I think because it's plotting. Let me undo that. Select data, and we're going to just get rid of all this. Okay, I'm going to do it the old-fashioned way. The X values I want are wing loading, so I'm going to come here, collect those, and the Y values I want are thrust to weight. There. And let's see, horizontal category access label. Sure. We'll call that, whoops, it doesn't like it. Am I done? Okay. That's what I want. That's what I want. I want wing loading along the horizontal and thrust to weight on the vertical. So let me see if I can't go in here now and let's select data. It won't let me. Why won't it let me? This is Super Cruise. And I'm trying to get the horizontal category axis label, but it won't let me select it. I don't know if that's a function of me or a function of what I'm doing. So let's go back to chart design right up here. You can kind of pretty this up. And we can do a quick layout. I like the quick layout because what it allows you to do is generate a format that you can quickly work with. There we go. So let's do this. Access title. If it doesn't want to let me hard code it, we'll say weight at takeoff versus planform area, and access title is thrust at sea level versus weight at takeoff. How about that? And so there's the first line of my constraint drawing. Let's go back to Jet 10, and you can kind of see now these curved lines, and there's cruise right there. There's cruise. This is acceleration, takeoff, land. There's so many phases of flight that we need to consider. And I didn't really say this when I started, but this ends up being your design space. This ends up being your design space. And anything above these lines and to the left of this landing line meets the constraints. Anything below that violates the constraints that were set forth by the customer. So that's how we do that. Okay. Any questions? Of course not. You're watching a recording. How could you possibly have questions? Now, why am I still in drawing mode? Are you serious? From this other Excel window, I have drawing mode. I can't, that's unbelievable. Okay, so I'm just gonna set that over here for now. So there's another condition called the combat turn. And so the easiest way to do this, um, and as I'm talking, I want you to know that there is a more efficient way of doing this. You don't have to constantly program constants. Constants can be just fixed values on your spreadsheet and you reference them. You don't have to actually program them all the way down. So for what's changing here? Now what's changing is our combat turn mock is going to be 0.9. I'll just drag that puppy down there. Okay. 0.9. Our alpha is 0.5. Now I can do this one of two ways. I can set that equal to that and then just change the first value and drag it down. Okay, that's one way to do it. For beta, beta changes to 0.8. I'm going to do this way so next time I don't have to copy paste, it'll just automatically populate. What's the combat turn? We're going to pull our turns at approximately 5.2 Mach. I'm sorry, load factor. Well, that would be kind of interesting, 5.2 Mach. What is CD0? CD0 is 0.0167. Okay, and I need to, okay. What is K2? I'm sorry, K1. K1 is 0.167. Okay. We're still at 30,000 feet, so my local speed of sound and density doesn't change, and I expect my velocity to have changed to about 895, and it does. Q changed. Am I climbing DHDT? Nope. Am I accelerating DVDT? Nope, that changes. G stays the same. CDX, no. That's for external stores. CD0. And K2 did change. There is a K2. Negative 0.01. 0.01. I'm working on MacBook using Excel through Office 365. So there may be some features that are slightly different than yours. Okay, let me double check everything. So alpha 0.5, beta 0.8, Mach is combat turn Mach is 0.9. The local speed of sound is 994.8, velocity 895.32, Q 37.11, K1 is 0.167, K2 is negative 0.01, load factor is 5.2, CD0 is 0.0167, CDX for external stores is 0. Acceleration of gravity is 32.17. DHDT 0 and DVDT 0. So I get values for my varying you can kind of spot check this and you can see the cells it's referencing. I think I might be off somewhere. Let me go ahead and plot this. Okay, so on the plot, I'm going to right click, select data, Now, the horizontal axis doesn't change, right? So I'm going to add a data set, and my x values don't change, and my y values do change. I'm not comfortable with these numbers because I'm also looking at somebody else's work. And what's this called? This is going to be combat turn. And this is supposed to be rising and getting bigger, but it is not. Why is it flat like that? Ten to 130. Alpha is 0.5. 0.8. Mach is 0.9. You know what? It might be, let's see. It's either the pre-quiz. No, that's the pre-quiz. That's the pre-quiz. No, it's the homework problem. So I am at a loss here slightly. I think there's an error somewhere. This turn right here, the combat turn information, I think it should make a line something like that. And that's why I'm questioning these results. Let's keep going because I don't want to. I wonder if it has something to do with my copy pasting here. Am I referencing anything else elsewhere? I don't think so. Q, does Q change? Does density change? No, density stays the same. And Q is properly calculated. The last one is for a level acceleration. So now you know that for level acceleration out here in dB/dt, right, that's the acceleration column, we're going to be at 13.93. And I believe, if I remember right, there is an acceleration calculator. There is an acceleration calculator here. So on jet 10, there's a piece of S, and oh, here it is, dB/dt right there. There's an acceleration calculator right here that you can help use to calculate your values. Okay, so you're going to repeat this process, and you're going to end up with a chart that looks similar to, if you haven't seen it yet, Dr. Brandt and Colonel Wickert published it. It's right here. This is what you're going to end up looking like. Now, I also want to show you what a more efficient manner of populating. It's a little more complicated because now you have to do cell references with the ampersand so that you don't change when you drag the thrust to weight equation down. But here's the same equation. Now, the way Colonel Wickert did it is he put his solutions here in these cells, and then he plotted those values, and he held wing loading constant. I'm sorry, the values consistent for all calculations of these phases of flight: supercruise, combat turn, level acceleration, takeoff, and braking. And he also can't. Let me see if I can scroll down for you. There you go. Here is the wing loading condition I'm sorry, the thrust to weight condition, more accurately, the thrust to weight condition. Back here to constraint for takeoff right here and for landing right here. And those equations get you the vertical lines. Actually, the landing equation is really what you're using. This vertical line is the landing equation, which is here. Yeah, I believe so. The takeoff line, which is here, is this equation there. And you'll plug those into your equation when you're calculating. And you can see how now the equation is much shorter, obviously. But once you've gotten used to programming it, all you do is you're going to program this equation into your thrust to weight cell, and then insert the values from phases 5 and 4, as Colonel Wickert showed you here. Now, the way I did it is still certainly the way to do it, but you can see the difference is largely a giant table of constants, and you don't have to do that. You only need to really make a table of what's changing. So there's different ways to attack this. Eventually, you're going to end up with a plot that looks something like this. And I can't figure out why my thrust to weight answers don't match Colonel Wickert's. And there's something in here that's going to take me a minute to figure out. But I'm not going to keep this video going. So you can make 5 different tables, one for supercruise, combat turn, level acceleration, takeoff, and landing. Or you can do a more efficient approach by just varying only those numbers that change, which in our case is wing loading. Everything else is constant. Now, when you do that, you have to make a cell reference. Uh, the F4 button will help you do that. If you type in an ampersand, it locks the cell reference. If you don't know what that means, ask a buddy. If you don't have time, you can do it the way I did and build a table. And then just reference each of those cells as you go across. All right. I am going to be out of the office tomorrow. Unfortunately, this is why I'm going to record this lesson for you, but hopefully you understand that the constraint analysis is an important tool so that it gives us a design space in which to work. And we will talk more about it in class, but I won't see you again until Wednesday. Please feel free to shoot me any messages. Colonel Wickert, Dr. Brandt could also answer questions for you if I'm not available. But please go through the exercise. It's important for you to become familiar with both how the constraint analysis and the constraint diagram are built and to build up your Excel muscles. Thank you.